Hello and welcome to another lesson in the Advanced C# course here on Tuts Plus. Now in this lesson and the following lesson, I'm going to take you through one of the typically more complicated topics to understand within any sort of language, but in your development career that you're going to run into probably, and that has to do with parallel or asynchronous programming, which really just at the end of the day means I want to be able to execute multiple instructions on a CPU or on multiple core CPUs at the same time. Now, in previous versions of .NET and C#, we were forced to do this through the system.threading namespace, and while this was able to get the job done, it required us to write a lot of overhead code in order to create these threads, spawn them off, have them execute some sort of operations, check when they're done, pass into them some sort of delegates or something of that nature to execute when they were done, or function pointers to execute when they were done. And so there was a lot of overhead there that we were really required to do in order to just really get things going. And then heaven forbid you had to do any sort of synchronization and making sure that you were letting go of resources when you were supposed to and not having any deadlocks and things of that nature. It really got to be quite a mess and really a headache to maintain, and really a lot of people shied away from it because of that. Also, one of the bigger problems with using raw threads in that way is that it is possible, if you were running on an older machine and you simply had a single core processor and you tried to spin up a bunch of extra threads to try to run several operations at the same time, you could really overload and actually, to the detriment of your application, cause a lot of context switching on the CPU between those threads because it was trying to execute them as parallel as possible, but since there was only one core, it could only execute one instruction at a time, and it had to switch between them. So that is very costly to your CPU, it's very costly to your system, and actually winds up typically slowing down your performance. Microsoft took a lot of these things back to the drawing board and said, how can we improve this? How can we give our developers the opportunity to continue to write asynchronous code, or code that can be run in parallel, but get rid of a lot of that headache and make it more intuitive to how they would typically write code today? So in this lesson, I'm going to take you through the Task Parallel Library, or TPL, and show you how tasks are able to alleviate a lot of that stress and a lot of the problem with writing parallel code and allow you to do it quite easily. All right, Visual Studio, here we are. We're going to select File, New Project, Console Application, and click OK. Now, I do have to do a little bit of setup here. As you know, in the previous lessons, I tend to write some code and then I'll hit Control F5, and that really runs the application in debug mode so that there is a line at the end of the console application waiting for you to hit any key. But at that point, it's kind of blocked all of the executions of any other threads or anything going on in the background, and we're not able to see anything else execute. So in order for me to properly show you some of these techniques that I want to show you, we're going to have to shy away from the debugging aspect and using Control F5 and just write our own sort of stopper at the end of the application so we can stop the console application from finishing but still allow us to see some code being executed on other threads or other tasks. So in order to do that, I'm simply going to drop down a few lines here, and I'm going to do a console write line and write in here a press any key to quit. And so this is really going to serve the same purpose as the Control F5 did. And after this, I'm going to say Control or Console read key, which is going to sit here and wait for keyboard input from the user. And it will sit here, not blocking, waiting for me to press anything on the keyboard. So if I were to hit F5 at this point, you're going to see press any key to quit, and it will just sit here indefinitely. And I can hit any key on here. I'll hit J, and the console goes away. So this is going to allow me to write a little bit more code so you can see things execute as we go. So what does the TPL, or the Task Parallel Library, do for us that threading couldn't do? Or how do we actually use these tasks that are in this library for us? Well, it's quite simple, actually. So the first thing I want to do is I want to create a task, and I'm going to call this T1. And I'm going to say this is equal to a new task. And if you see here, there's a number of overloads, but the most common one, at least for this course, is going to be the action. And if you recall from our lessons on delegates, anonymous methods, and lambda expressions, this is merely a generic delegate, and since there is no generic parameterized type on this action, that means there are no inputs to this. So let's go ahead and check that out. So what we can do is we can create a lambda expression, which is where I'm more comfortable with. And since we don't have any inputs, that means open and close parentheses with nothing in it. We have our lambda operator here, the equals caret symbol. And then we need to do something in here. What is the task we want to complete? Well, we could do a number of different things, but I'm simply going to create a very simple lambda expression here. And I'm going to say here that console write line task 1 is beginning. And then I will do some sort of thread sleep here just to kind of pretend that there's something else going on here in the background. And thread.sleep, if you're unaware, is in the system.threading namespace, and it is left over from much earlier versions of the .NET framework. But really, it's quite simple. It just takes in a number of milliseconds that you want it to sit here and wait. So I'm going to give it 1,000, which basically means I want you to sit here for a second. And then I'm going to do another console write line, and it's going to say task 1 has completed. So there we go, I'll save that. All right, so now we've created our task and we've given it an action, what we want it to perform. And so now let's see what happens. Let's hit F5 and we see press any key to quit, but it doesn't look like anything's actually happening here. And that is exactly what I would expect and what you will be coming to expect when you create a task in this way. Now, there are other ways to create a task, and I'll show you that in a few moments. But when you create them in this way, they don't start automatically. You have to explicitly tell them to start using the start instance method. So now if we hit save and hit F5, you're going to see press any key to quit, but also that task 1 is beginning and task 1 is completed. So that was fairly quick. It was only a second in between. But if you see, if I had this sleep for, say, 2 seconds, and hit F5, it'll sit there a little bit longer. Task 1 is beginning. Task 1 has completed. Okay, well, that's not overly interesting. What's that really doing for me? Well, nothing in its current form, because I'm not actually having this application do anything else while these tasks are executing. But where the task parallel library and tasks really start to shine is when you want to do multiple things, multiple operations, or even multiple tasks at the same time. So what I'm going to do now is I'm going to refactor this a little bit, because I'm going to want to share this code between multiple tasks, but I don't want to just copy and paste this because, as you know from my previous lessons, I can't stand duplication of my code. So what I'm going to do here is I'm going to create a new method, a static void method that's called do some very important work. And I'm going to pass in a couple arguments. I'm going to pass in an int, and it's going to be an ID. And I'm also going to pass in another int that's going to be sleep time. So I can configure this across multiple threads, or multiple tasks, excuse me. So then I'm going to cut this logic out of here. I will paste it in here. Now I'm going to do a little bit of formatting in here. Nothing you haven't seen before. And this is going to be the ID. And then we are going to, instead of hard coding to 2000, we're going to call this sleep time. And then we're also going to format this console write line with the ID as well. So we'll save that. And now in our lambda expression up here, we can get rid of these curly braces, since we're really only going to call one method here, and it's going to be the do some very important work. And this task, this is the only job of this task, and we're going to call the ID 1 and the sleep time 1500 milliseconds, or about 1.5 seconds. So there we go, save this, and if we hit F5, we should see the same basic functionality. So nothing here too out of the ordinary. So now what I would like to do is I would like to show you how these things begin to execute in parallel given the opportunity. So in this case, I'm just going to copy these 2 lines. I'm going to copy, I'll paste 2 more of them here. So now I'm going to have a T2 and a T3, do some very important work. This is going to have an ID of 2. This is going to have an ID of 3. And instead of all waiting the same time, this one's going to execute in 3 seconds, and the third one is going to execute in merely 1 second. So then I have to change my start methods here to be on T1 and T2 and T3. So now if I save this and hit F5, we're going to see something a little different. So we saw press any key to quit, and then we saw all of the tasks beginning at once. So you can start to see that parallelism. And then once that sleep timer has been completed on all of them, you see that task 2 started, but task 2 was the last one to complete. 3 started, and then 1 started, and then they finished in 3, 1, 2 order. So as you can see, based on that sleep time, based on the logic that they're executing or how long it takes is how long these threads, or how long these tasks, I should say, are going to execute. Okay, so you can start to see how these things are beginning to work a little bit now, and you could spin up as many of these as you wanted. Now, in this case, I'm probably not being as optimal as I probably could, since there's not a lot going on in these. I'm really only calling one method here, and I have to write 2 lines just to do that. Well, there's another way that you can create tasks and have them execute immediately, and that is via something called the task factory. So the way that we use a task factory, I'll show you quickly here. On the task class, we have a factory, and there is a static method on here called start new, which takes the exact same arguments as you would if you were creating a new task. So you can execute these the same way, but the only difference here is once you have called the start new method, it will create this task and execute it all in one step. So let's go ahead and modify our code a little bit to take advantage of this and stop doing unnecessary steps. So all I'm going to do here is remove this line and change the new task line here to a task.factory.startNew. And now I can get rid of this start, and I can do the same for these as well. And change this. I'll copy and paste and paste. Now I can save this and hit F5, and we get the same functionality. We have 231, 312 completing. So as you can see now, I've taken those 2 lines to create and start a task down to 1. So that's kind of a nice little optimization. So what are some other common things that you're going to find yourself needing to do when doing asynchronous programming or working with these tasks? Well, oftentimes you're going to want to do some very important work, which is going to be some setup work for another task altogether. So how would I start to chain these things together? Well, there's absolutely a mechanism for you to be able to do that within the task parallel library, and it's called continuing. So let's say that after I finished this, do some very important work, I had to do another method or some other form of operation, and we're going to call this do some other very important work, and we're going to take in the same properties here, but this time we're going to say task 1 is beginning more work, and that task whatever has completed more work. So now we're going to save this, and the way that we start to do this, the way that we start to chain these things together is via a method called continue with. So once I have created a start new, as you can see, the return type here is a task. A task has a concept of a continue with that I can chain onto the end of this. So I can say dot continue with, and this is going to take in another task or another action that has a task parameterized type. So the way that we do this is similar to how we would any other generic delegate. We're going to create a lambda expression, and we're going to have a reference to a task here. So we'll say previous task or prev task. This is going to execute another operation, which is do some other very important work. And I'm going to pass in 1 again for this guy. And this time he's going to take in a second to execute. So then we can save that. And now I'm just going to copy this continue with statement. Well, actually, for now, I'm just going to leave it on this one so you can see that the other 2 threads are going to, the other 2 tasks are going to complete, but the first one is going to continue with a secondary operation. So now if I hit F5, you're going to see that they're all starting, and that task 1 has completed, and that it also has begun doing more work, and it has completed more work, and 2 finished its normal work. So you can see that you can start to chain these operations together, and continue with also returns a task object. So I could chain another method on the end of this if I wished. I could continue to do this all day if I wanted, and I could start to build these hierarchies and this chaining of tasks together so that once the first operation is completed, it can follow on with the others as well. So if I were to go ahead, like I said before, and copy this continue with, copy, and do a paste, and then I could add in here, this is a 2 and a 3, and then we'll do this one at 2 seconds, and this one at 500 milliseconds. And we can save this, and once again hit F5, then you're going to see all sorts of work starting. You know, task 3 is completed, it's beginning more work, so they all have more work to do once they have finished their initial task. So that's a really nice feature that Microsoft has added here that really makes it easy to, instead of having to detect when a thread has completed, we can now just pass additional tasks in there to be completed or additional operations to be completed on another task once the first one is complete. So that's kind of nice. So now you may be saying, well, that's great and all, but I don't always have the luxury of being able to chain these things together and continue to execute these. What if I need to execute these one at a time because they're doing very important tasks at the same time, and once they all are completed, I want to be able to know when they're done so then I can finish the operation of my method or whatever my code is and move on to the next step. So in order to do that, another concept that was kind of brought over from the system.threading days was the concept of waiting for tasks to complete. So how do we wait for these tasks to complete? So just to show you an example, if I were to hit F5 again, you notice that the press any key to quit console write line executes actually first before these other tasks are actually started. So what if I wanted to wait until all of these tasks were completed before I actually showed this console write line and the read key? Well, that's quite simple. The way that we're going to do that is via another method on the task class, and that is either wait all or wait any. So wait all is going to take in an array of tasks and wait till all of them have successfully completed before continuing on the execution. So you could think of this as a way to block the execution of this application until all of the things or all of the tasks specified within the wait all parameter list have completed. So let's go ahead and try that out. So I can say here var task list is equal to a new list of task objects, and I'm going to put T1, T2, and T3 all in here at the same time. And then I will do a task.waitAll task list.toArray and go ahead and execute this. Now if I hit F5, you're not going to see that please hit any key to quit method until, or that line, until all the tasks that have been added into the wait list have executed. So that's kind of nice. So now you can see that, well, yeah, I can do that and wait for everything to finish. That's great. But what if I need to do some other work on my main application code base, but also have these tasks going on in the background? Well, that's the beauty of this. You don't have to worry about that. It's all being taken care of for you. So if I just comment this out temporarily so I can show you a little bit of how this also looks if I have other operations going on. Let's say that I spawn off those tasks to do some sort of other work to bring me back data. But while I'm doing that, I can be doing other things. I could be processing other requests, or I could be doing some other sort of business logic here. So for that instance, let's just say I have a for loop here just to imitate some sort of work going on. We'll say I equal to 0, I less than 10, I plus plus. And within here, I'm going to say console write line, doing some other work. And then I'm going to have this thread sleep for about, we'll say 250 milliseconds. And then I'm going to do a console write line formatted slightly here. I equal to an input parameter, which is going to be I. So we'll save this. And now since we've commented out the waiting, we're not waiting for these things to finish anymore. So all of the other code in our application can continue to run. So if I hit F5, you're going to see we're doing some other work and we're iterating through the I's while these other things or while these other tasks are executing until everything has finished and we've come down and nothing else is left to run. So just as we did before, if I needed to wait to execute this logic because it was based on things that were being finished by these tasks, I could merely uncomment these lines and I could hit F5, and now we're not going to do that other logic until all of these tasks have completed. Now I'm going to do this other work where I need to iterate through 10 integers or something of that nature. So you can start to see that just writing this asynchronous code now has become very easy and actually very familiar to us in the ways that we have simply written our normal non-asynchronous or non-parallel code in the past. So I hope you're starting to feel a little bit more comfortable with the concept of tasks here. Now I want to introduce you to another topic that was introduced within the task parallel library, and that is the process of being able to do certain looping functionality in a parallel manner as well. So if you've recalled in the past when you had, say, a lot of data to churn through and you had to loop through them and do some sort of operations on them, it took a long time because you had to do those all sequentially. So let's take a look at how that has been alleviated within the task parallel library. So let's say we have a list here, and it's going to be an int list, and it's going to be a new list of integers. And let's just start to bang on the keyboard here a little bit to generate some data for us. Something like that. And now I need to churn through all of these and do something with them. So in the case of this concept of going through all of the objects within this list and executing some sort of logic against them, we are going to use the parallel.forEach method. Now if you take a look at this, it needs a source. So we need to provide it the source of data that we're going to work through, and that just happens to be our int list. And now we need to give it some sort of action whose input, as you can see here, it sees that this int list is a list of integers, so it knows that the input into each action here is going to be an integer. So we're going to provide a generic delegate via a lambda expression, and it's going to take an input, and it's going to take an integer input. So in this case, we're going to call it I. And it needs to execute some sort of operation. And we're going to keep it rather simple here, but we're going to do console.writeLine. It's simply going to write I out to the console. Now I want you to pay close attention to what happens when I execute this, because you may expect, because this is a task, because this is the task parallel library, that you will see press any key to quit before we've seen the end of this loop. So let's go ahead and hit F5 and see what happens. So now as you can see here, it didn't actually happen. And as you can see, if you look very closely, the integers found within this list are not being written to this in order. So I see 1, 2, 6 instead of 5, and 5 isn't until later on down here. So things are being spun up and executed asynchronously. But interestingly enough, the press any key to quit happened after the execution of the parallel for each loop. And that's because the parallel class and the methods that are written off of it, namely for each, invoke, they are all thread blocking. They are all blocking operations. So you will not continue beyond this line until everything within there has completed. So there's almost like a built-in wait all happening here to stop any sort of execution of any other code before this loop has completed. So that's definitely one thing to keep in mind before you start to add this to your code, that if you think you're going to write this and other operations are going to complete, that's definitely not going to happen. So let's take a look quickly at the other common method here, which would be the for method. So parallel for, you can see here, this is mostly meant for allowing you to pass in a range of values that you are going to wind up looping through and doing some sort of action on. So let's say we wanted to run 0 through 100, and we want to do some action on that, and we're going to pass those in as I, and we're just simply going to once again do a console.writeLine to write the I value out to the console. So now we'll hit save, and if I were to execute this with F5, you're going to now see that it's going to print out in parallel 0 through 100 inclusive, but you're definitely going to see that these are done in parallel because it's nowhere near in order. They kind of bounce all over the place with no regard for order. And once again, we see press any key to quit at the very end, which just further solidifies the fact that this is a blocking operation, and anything that is after this is going to have to wait until all operations done within this parallel for loop have completed. Okay, so now that I've kind of taken you through the basics of creating tasks and how they execute and how you can execute things in parallel, and also how to use the parallel class and the for and for each loops to execute operations on multiple values at the same time, I want to take you through one other concept as far as tasks are concerned that oftentimes do come up that you will eventually need to handle in your code, and that is what's happening if I'm executing these tasks but I need to stop them from executing because something has happened. I need to halt these operations, clean some things up, and either carry on with the rest of my application or completely exit out of everything. Well, the way that we do that is through something called a cancellation token. So if I clear this out up here and I start to recreate some of the things that I've done before. So let's say I create a T1 and it's going to be equal to task.factory.startNew. And it's once again going to take in an action, and it's going to be as it was before, do some very important work. And this is task 1, and I want it to wait for 1200 milliseconds. So this is basically what we did before, not a big deal here. And let's say that we were going to do this operation and we wanted something to happen in here, and we wind up wanting to chain these operations together with previous task. And when this is done, I want it to execute the do some other very important work again. And this is going to once again be 1 and say 3,000. Okay, so I can save this. And so now let's say that something happens while I'm doing this very important work, and I need everything to just quit. I need to pop out of all of this stuff and continue on with, do some cleanup or continue on with some other operation. How do you do that? Well, as I mentioned before, you do that through what is called a cancellation token. Now, there's a couple of different ways you can handle this, but I think the more common way is to create a cancellation token source. So let's create a reference to that. So let's create a variable called source. It's going to be equal to a new instance of a cancellation token source. Now, really all this is just a way for you to have a reference to this throughout the execution of your code, that if something happens at some point, I want to signal to everything, all tasks throughout my application, that they all need to halt because I need to do something else. And that's going to be done through the token that you can generate through this source. But one thing to keep in mind is that this is not magic. If you need to handle some sort of cancellation token within your code, you are required to do it manually. It is not done automatically. You have to be checking for a cancellation signal. So the way that we do that is we're going to modify our do some very important work here, and I'm going to pass in a cancellation token. We're going to call it token. So we'll do a save. And now the way that we handle this within our code that's being executed is we have to periodically check to see if our token has had a cancellation requested. So if our cancellation has been requested, we want to, just to show that what's happening here, we can say cancellation requested. And then typically what you would do at this point, since this is only just signifying that something is to be canceled, you need to actually do something with that, is typically you're going to do a token.throw if cancellation is requested. So really what this is going to do is it's going to see if a cancellation has been requested, and if it has, we're going to write to the console, and then we're going to throw out of this. And this is actually going to throw an exception that you're actually going to wind up having to catch within your code. So this is not uncommon to see when you're working with tasks and you have to handle some sort of cancellation. We can do a catch block here, or actually we'll just do a finally block, since I will add a catch in here just for illustrative purposes. We're going to catch an exception, and just to show you what type of exception is being thrown. So I'm going to do a console write line ex.getType like that. Save, and now I'm going to get rid of my finally. So now what I want to do is I want to execute this code in my try block, and I'm going to create this source up above just so that it's outside of the scope of this try catch so I can access it anywhere. And now I need to be passing a token into my do some very important work method. And the way that you do that, you can create it explicitly. You could say I want to create a new cancellation token, and I can pass in a value of whether this is canceled or not, but you're kind of losing the power of being able to trigger the cancellation, which is what you can do within the source. So what I'm going to do here is I'm going to call the source.token property, which is going to pass a token generated by this source into our very important work method. Okay, so we can save this. And so now if I just leave it like this and I hit F5, everything is going to continue to work as it was. Task 1 is beginning, it is completed, it's beginning more work, no big deal. But now let's say I start to do this work, but as soon as I wanted to start this, at some point in my code I have this source and I need to cancel the operation of this, so I can call the cancel method and hit save and hit F5, and now you can see that the operation was canceled. So if I hit F5 to continue execution, you're going to see that it saw that I was canceling that request, but unfortunately because I didn't stop it fast enough, everything continued to execute because I caught on that line. But you're starting to see like how I can detect if a cancellation has been requested, and if something has been requested, I can dump out of this work method. And really, to be complete, to be honest with you, I should be passing in a cancellation token here as well, just to be as explicit as possible, and I will do the same operation here. I will copy this. So just in case, in that similar instance as before, if I'm not catching it in time, if it tries to continue on with the next operation, in that case is the do some very other important work, it will dump out of there as well. So I can say token. Now I can save this. And now if I hit F5, you're going to see that it caught this exception, and I can hit F5 and it caught it again in the other method. And so it caught that each of my methods of operation caught the fact that a cancellation was requested. So just because the operation of that task makes it into your code that needs to be executed, if you catch the cancellation request in such a way, you're going to stop all of the execution of all of those things. And since these are quite simple, this is not very difficult. If you catch it just as it goes in, then you're fine. But in other applications, depending on how sensitive you are to these cancellation requests, you may have to put some checking periodically throughout your code to make sure that you're not going too far before you're handling that cancellation request. So that really has kind of been a nice little overview of what the task parallel library is, how to work with tasks, how to handle the cancellation requests of tasks, and how to use the parallel.for and for each loops. So I hope you found this very interesting, and I hope you start to think about some ways that you can incorporate this into your code, especially if you're still using the old system.threading namespace. Now, I'm not bad-mouthing it because it's made it to this far, and it's still in the framework, and you can still use it in C#. And I think that's a testament to the power of it, but it's definitely something that's rather difficult to deal with, and there's a lot of overhead that goes into it. Whereas using the task parallel library, a lot of that headache and that functionality of having to figure out, should I spawn a new thread or should I not, or should I reuse other threads that are just idle and waiting, all of that stuff has been wrapped within this concept of a task, so you don't have to deal with that anymore. It has been optimized for execution on machines that either have multi-core or single core or dual processors or anything of that nature. So definitely play around with this, see where you can put it into your day-to-day activities, and I hope you use it tomorrow. I'll see you in the next lesson.